Good morning. So just try to settle down as soon as possible, and we'll start our lecture today. Did you all watch a video the TA gave you last week? Okay, that's good. You know this is an English lecture, right? So you still have time to drop it and join another class if you want. Okay, so last week in the video, we show you a few examples of a 2D mechanism. And we try to use the equation to define the mobility of certain mechanisms. And let's just take a quick review of the last example I showed you last time. So if you still remember, we use the equation. I'll just write on the slides. So use the equation to determine the mobility. Sorry, just okay. So use the equation to determine the mobility. The equation, I think, is fairly simple. So the equation is in this form. So it's basically 3 times n. N is the number of links. So for example, in this mechanism, we have a ground link, and 2, 3, 4, 5 is a slider, and 6 is the bar. So we have 6 links in this mechanism. So for this case, n is 3 times 6 minus joint. And how many joints do we have in this mechanism? Let me change the color. So you have one R joint here, and the second R joint here, third R joint, fourth R joint, fifth R joint. So 5 R joint. R joint means the revolute joint. So it only allows rotational motion. We also have one slider joint here. So I label it as 6. So this one is sliding joint. Okay. And we have one more joint, which is this one. And this one, it says there's no slippage. So that means it's pure rolling. So pure rolling joint is also what? It's also a joint. And it's also a 1 degree of freedom joint. So I label it as 7. So we have 7 1 degree of freedom joint. And I'll change the color back to red. So 6 minus 7 and minus 1. Do you remember the meaning of this minus 1? Yeah. That's a ground link. The ground link has no degree of freedom, so we need to subtract the ground link. Okay, so we also need to add we call it connectivity. So because in this equation, originally we assume all the joints will constrain all the degree of freedom. But actually, those R joint or the sliding joint, they all allow 1 degree of freedom. So we need to add them back. And in this case, because all these 7 joints, they are 1 degree of freedom joint. So we need to add 7 back. So you can calculate it. You 3 times minus 2, so minus 6 plus 7. So you'll get 1. So mobility of this mechanism is 1. Yeah. Any questions so far? No? Okay, so the example I just showed you is a 2D mechanism. But how about a 3D mechanism? We won't talk too much about 3D mechanisms, But here, you just get an idea. If you have a 3D, or we call it spatial, that means it's in a space, in a 3D space. If it's a spatial mechanism, then how can we find the mobility of the mechanism? So you'll find the equation is very similar to the 2D case. The only difference is we put a 6 here instead of 3. Well, because meaning in a planar, for planar mechanism, we know each link we add to the plane. Originally, if there's no constraint, the link should have 3 degrees of freedom. It can move in X direction, Y direction, and it can also rotate. So there are 3 degrees of freedom for a planar link. But for a spatial link, in a space, well, you can move in X, Y, Z direction, and you can also rotate in the X, Y, Z direction. So there are 6 degrees of freedom in total. So the only difference in the equation, well, is the 6. We use 6 instead of 3. And the rest are the same. It's also the number of link and the number of joints, and -1, which is the ground link. And we also need to plus the connectivity back. Depends on how many degrees of freedom a joint contains. Okay, any question about this, this equation? Okay, so let's just try to do an example. This one is a spatial mechanism. Okay, so there are 4-bar. It's also a 4-bar mechanism, but we call it a spatial 4-bar mechanism. We also have a ground link. It labels all the links here. So we know there's a ground link. We label it as number 1, and there's a link here, number 2, 3, and 4. So 4 links in total. So let me just write down the equation. We have 4 links. 4. We also have 4 joints. It labels all the joints for you. It's a spherical and spherical joint, and this one is a revolute joint. This one is a cylindrical joint. So also 4 joints. 4 joints. And -1 for the ground link. But we also need to add the connectivity back for all these 4 joints. So the connectivity means how many degrees of freedom does a joint contain. So how many degrees of freedom can we find in a spherical joint? Do you remember? I think in one of the slides we covered different type of joints, and spherical, because spherical joint is basically, we also call it a ball joint. It's a ball, and you use a shell to constrain the ball, but the ball can rotate in any direction. Right? So this spherical joint contains 3 degrees of freedom. It means 3 rotational. It can rotate about 3 different axes. So this one will have 3 degrees of freedom. And all the degree of freedom is about rotational motion. So 3 degrees of freedom. Also 3 degrees of freedom for this joint. And there's also a revolute joint. In both 2D case or 3D case, revolute joint always allow only 1 degree of freedom. You only allow the rotational motion along one single axis. So this revolute joint is 1 degree of freedom. How about cylindrical joint? Cylindrical joint allows rotational motion, but also allow sliding motion along the axis, along the central line of the cylinder. So this one, this 2 degree of freedom joint is 1 rotation. This rotation plus a sliding motion. So for this case, we need to add all the connectivity into the calculation of a mobility. So a plus 3, plus 3, plus 1, plus 2. So you'll get minus 6, plus 3, plus 3, plus 1, plus 2. So you'll get 3. So for this mechanism, we'll get mobility for this mechanism is 3. Yeah. Any question about this one? All good? Okay, here I only show you one example of the spatial mechanism. We won't talk about, we don't talk about the spatial mechanism too much. We'll mainly focus on the 2D case. And so here we back to the 2D examples. Usually we just use the equation, the mobility equation, to find the mobility of a mechanism. But you will find in some mechanism, sometimes the mobility equation will give you incorrect answers. They include 3 cases. One is we call it idle degree of freedom. Don't worry about this too much. I'll show you in the following slides. Also, another one is called locally over constrained linkages. And there's another case. Is usually when we consider a mechanism, sometimes even, you know, in the real world, all the mechanisms should be a 3D mechanism, right? Yeah. But sometimes when we calculate the mobility of mechanism, we consider it as a 2D mechanisms. And that's just for some convenience for us to calculate the mobility. Well, I'll show you an example. If you consider a mechanism as a planar mechanism, and you will see, you will get different result by considering it as a planar mechanism rather than a spatial mechanism. Anyway, we'll see that in the following slides. Okay, so for the first case, it's called idle degree of freedom, and there are some description here. I just read it. So it's possible to move a link or a subset of links without changing the input-output relationship for linkage. And to determine if an idle degree of freedom exists, determine if you can move one link without moving any other part of linkage. Or you may still be confused after you've seen this description. So let's just take a look at this example. So the left-hand side shows you an example of a spatial mechanism. And there's one R joint here. It's an R joint. And there are 2 spherical joints. They're very similar to the previous case, previous 3D mechanism we showed in the previous slides. So we use the mobility equation to find the mobility of this spatial case, spatial mechanism. So there are 3 links in this linkage, and also, 4 links in this linkage. Also 4 joints in this linkage, 2 R joint and 2 S joint. S means spherical joint. We also need to subtract 1 for the ground link. And we need to plus the connectivity back. If you still remember, each spherical joint will add 3 back. So plus 3, and for each R joint, we'll plus 1 back. So for this one, we'll get the mobility equals 2. So what's the meaning of mobility equals 2? That means if we move, we need to define 2, in this case, we need to define 2 variables in order to define the position of this mechanism. But actually, if you, it might be a bit difficult for you to imagine, but if I define, I call this one angle theta, and this one is phi. If you build this mechanism and you rotate this theta, you'll find this phi will also move correspondingly. But so it works like it's mobility equals to 1 rather than 2. If you build this one and you try to move it, once you move this theta, this phi will also be defined. But it's like the if you still remember in the in the planar 4-bar mechanism, if I move this theta 2, this theta 4 will also be defined, right? You don't need to define another parameter in order to define the position of this mechanism. You define theta 2, then you will directly get the theta 4. In this case, it's very similar. You define the theta, you will get the phi directly. You don't need to define another parameter. But we get the result, the m equals to 2. So from this equation, we assume we need to define 2 parameters in order to define this output angle. But if you really build this one, you define 1 parameter, you will get another, you will get the output value. So it seems like it's m equal to 1 case rather than m equals 2. Then where is the extra degree of freedom? So in this case, we call it idle degree of freedom because the degree of freedom happens here. You can rotate the bar 3 in this direction, but it's useless. It's a useless degree of freedom. So this mechanism works like m equal to 1 case, but indeed it's actually m equals to 2. Yeah. But we know one of the degree of freedom is useless, so we call this degree of freedom idle degree of freedom. Yeah. But actually, it's not wrong if you get m equals 2 because m is equal to 2. Yeah. But just it's a useless one, so yeah, we just call it idle degree of freedom. And this one is very similar. You can try to calculate it by yourself. It's a planar mechanism. And you will find this small wheel. The small wheel here is useless. Yeah. You can rotate it in any angle, but it won't influence the input to the output. Yeah. Because this one is just a cylinder. No matter how you rotate it, it won't influence any other position, the position of any other links. Yeah. So the theta of this one, the angle of this small wheel is also idle degree of freedom. And the angle of this one, I call it alpha. So these 2 angles, they are idle degree of freedoms. So this is the idle degree of freedom. And if you use the equation to calculate the mobility, well, you may get unexpected result. So just remember, well, it might be this case. We have some redundant or some useless degree of freedom. So that's the first case of when we use the equation, you will get an unexpected result. Yes, please.
The second case.
Yes.
Which length is the input length?
Input. We didn't define the input, but well, you can either use this one as input or this one. Well, I think originally supposed to use this cam, so it's a cam follower mechanism. Yeah. So you rotate this one, this output will move correspondingly. Yeah. But you know, in every mechanism, well, you can either you can pick any links you want as input. Well,
And the outcome would be the same?
the outcome, yeah, the outcome will be this one. For my understanding, this mechanism, I think 90% of the case will use this one as input and this one as output. So as you rotate this one will move forth and back. Yeah. Okay, so the second spatial case is called over constraint, and or more specifically, it's called locally over constraint. What does this mean? So assume we have two mechanisms. One is this, well, basically it's a 4-bar mechanism, the 4-bar planar mechanism. We have 4-bar and 4 joint. And this one looks very similar to this one. Right? The left-hand side one looks very similar to the right-hand side one. But the only difference is this one contains only 4 links. This one contains 9 links and so many joints. I'll do the right-hand side first, and I think you're all familiar with it. So we have 4, it's a planar mechanism. So we use the equation 3 times 4 is a number of links. We have 4 links. We also have 4 R joint. Just label them 3, 4, 4 R joint. And minus 1 for the ground link. Also need to add 4 back. So you will get the mobility of this one is 1. And yeah, it is 1. Once you move this either link 2 or link 4, the other one will move correspondingly. Yeah. But how about the left-hand side one? Do you think this one is movable? No? It looks exactly the same as this one if you ignore the top part. Yeah. It should also work. If I move this bar 2, this bar 4 should also move correspondingly. So I think this one should be, the mobility of this one should also be 1. Do you agree with me? But actually, if you use a equation to find the degree of freedom, to find the mobility. So right now we have 9 links. And how many joints do we have? Well, there are a lot here. So let me change the color. So if 1 R joint 2. So how many joints do we have here? There are 4 links connecting to this point. So we know that the joint means, the joint defines the relationship between 2 links. But right now we have 4. So there are number 2, number 3, number 5, and number 7. So we need many joints to define the relationship between these links. So we need 1 to define 2 and 3, right? New define 2 and 3. What? Anyway, something wrong with my monitor. Okay, so we'll define, we need 1 joint to define the relationship between link 2 and link 3. We need another one to define link 2 and link 5. And another one to define link 2 and link 7. So I think we need 3 joints here. Now there are 3 joints here. Yeah, to define the relationship between the links. So 3 joints here. And here, this one is also 4 links connecting to this point. So also we need to define 4 and 3. Okay, I think it's my sweat. Okay, anyway, I use the mouse to indicate. Okay, so 4 and 3, and for 1 joint, and we need another joint to define 4 and 9, and another joint to define 4 and 8. So there should be 3 joints here. And how about this one? This one connect number 5, 6, 7 together. Oh, sorry, 5, 6, and 9 together. So we need one joint to define 5 and 6, another one to define 5 and 9. So there should be two joints here, and the same here. 6, 7, 8 are connecting to this point. So we need one joint to define 6 and 7, another one to define 6 and 8. So two joints here. So in total we have, I should write 1 here. So there are 12 joints in total in this case. So your 9 minus 12 and minus 1. And because all the joints are joints, so we'll plus 12 back, because each joint contains 1 degree of freedom, so we need to plus 12 back. But if you use this equation to find the mobility, you will get 3 times what will we get here? 9 minus 2, so minus 3, minus 1, minus 4. So we'll get minus 12 plus 12. So we'll get 0 here. 1, 2, 3, 4, 5, 6, 12. Yeah. So if we use the equation, we'll get mobility equals 0. But actually it's movable. This one, we can move this bar 2 and this bar 4 will also move correspondingly. And this top bar this coupler will also move correspondingly. Sorry. Yeah. So again, if we use the equation to calculate mobility, we'll find the incorrect answer in this case. But why does this, why is it happening? What caused the equation to generate wrong answers? You all agree this one has 1 degree of freedom, right? It's movable. Yeah, it's not a brick. It's movable. But why is this equation giving us a wrong answer? Let me open the blank slide. The reason is we consider too much constraint in this case. So I just So I just draw the top bar, this part. I just try to examine that part. So in this case, originally, well, if I consider this 4-bar mechanism, then we know the mobility equals to 1. We calculated it so many times. So we know mobility equals to 1 for this mechanism. And in the previous case, there's 1 additional bar put here to connect these 2 points together. Yeah. But once we add this bar here, do you think this mechanism is still movable? No, it's no longer movable. Then let's try to calculate the mobility. So you get m equals 3. Right now we have 5 bar here. So 5 minus, how many joints do we have here? So you have 1 joint, another one, and 1 here. Because here we have 3 bar connecting to this point. So there should be 2 joints here. 1 to define the relationship between 1 and 2, another to define 1 and 5. Yeah. So 2 joint here, and 1 joint here, 2 joint here. So in total, we have 6 joint here. And minus 1 and plus 6 back. So we'll get minus 6 plus 6, so n equals 0. But it is 0. This one is not going to move. Yeah, this one is totally fixed. But in the previous case, in the previous slide, we put another bar here. Right, we add another link to connect from this point to this point. But what happened to this link? I use another color to indicate. So this is 6 bar 6. So by adding this new bar, you'll get n equal to 6. And how many joints do we have? By adding this one, we'll add one more joint here and one more joint here. So it becomes 6 and minus 8 joint, minus 1. And we need to plus something back. And we need to plus 8 back. So by calculation, you'll get this equals minus 1. What does minus 1 mean? Well, the minimum should be 0. 0 means it's not movable. It's over constrained. It's like a brick. It's not going to move. But here we get minus 1. What does minus 1 mean? Well, it still means it's not moving. So the true meaning of minus 1 or minus something, it actually means the same thing as this 0. But when you take a look at this equation, well, because we add this new bar here, we add these new links here, in the equation you will get some over constraint here. So you'll get some minus item here. But when you put this minus back to the original linkage, you will subtract more than you expected. Well, it's not expected to have a minus value here. But if you just use the equation, you add that let me say, if I add one more link here, it didn't add any more constraint to this linkage because it's originally constrained. It's originally is not going to move. But for every link I add here, you will get the minus larger value here. Okay. But in reality, well, it didn't constrain any more stuff here. But it will cause some calculation mistake here. Yeah, so we call this this case. We call this over constraint because we add too many links, and by calculation, every link you add into this mechanism, you will add some more joint, but this joint will actually add more constraint in the equation. So that will result in some error answer, some wrong answer. Any question about this one? Yeah, so you can compare the top equation and bottom equation. For you add one more links here, right? But you actually need to minus 2 here because you add 2 more joints into this mechanism. You plus 2 back. So actually, the total effect of the link you add, the link number 6 I add into the system, I will get minus 3. I'll get minus 3 plus 2 for adding this number 6. Yeah. because you'll get 3 times minus 1 and plus 2. But actually, when you add these numbers, link number 6 into the mechanism, it's not going to influence the mobility of this mechanism. But mathematically, it will minus 1, which caused the mistake. Any question about this one? What's okay, so this is a final case. Well, I make a wrong title here. It belongs to the third spatial case. So the final slides I'm going to talk about is this. Planar mechanism are spatial case or spatial mechanism. Sorry, ignore the title. So suppose we have this mechanism. I think it's okay. So we have this. We only consider this this part. This is also a 4-bar mechanism. So it's bar 1, bar 2, bar 3, and bar 4. And this bar 1, also 4 joints here, 1 R joint, and this one, 2 and 3 is a sliding joint, and another R joint here. So let's try to calculate when consider this one as a planar mechanism. We can try to calculate the mobility. So right now we have 4 links. We also have 4 joints. And minus 1. Consider this link 1 as ground link. We need to plus 4 back because each joint will contain 1 degree of freedom. So R joint, and slide in the P joint and R joint. They all have 1 degree of freedom. So if we consider this one as a planar mechanism, we know the mobility is going to be 1. Yeah. And we know this mechanism is going to move. Usually we use this piston as an actuator, so you can move this cloud here. We use a hydraulic actuator, so it can move linearly to push this bar 3 back and forth. And then yeah, you just move the rest. But how if we consider this one as a spatial mechanism? For spatial mechanism, we'll have 6, but it's still a 4-bar mechanism, so the n equals to 4 and minus 4 joint and minus 1. But we need to add the connectivity back. And because this one is R joint, and P joint, so each joint contains 1 connectivity or 1 degree of freedom. So we'll add 4 back. But if you use this equation for spatial mechanism to calculate the mobility, you will find you actually will get 6 times minus 1. So you'll get minus 6 and plus 4. So you actually will get minus 2. So even the same mechanism, and we didn't change anything. We consider 4 links and 4 joints And the joint are 3 R joint and 1 P joint. P means a sliding joint. But if you use a planar equation, you will get m equals to 1. If you use a spatial equation, you will get m equals -2. But do you think this one is gonna move? It's movable? Yeah, you've seen this type of machine before, right? It should move. Yeah, it should work. It should not be mobility smaller than 0. So what's the problem here? We use 2 different equations, with a planar equation and use a spatial equation, but they gave us different result. Which one should we believe? I think we would believe this one because we know it's gonna move, so we believe this one. But what's wrong with this one? Well, actually, this one is not totally wrong. Right now, because all the links, they lie on the same plane. So we know there are 3 R joint, but all these R joint, the axis of all the R joint, they are pointing the same direction. But in this equation, well, it's not assumed that all the R joint, the axis of the R joint are pointing the same direction. If they are pointing different direction, this mechanism may not move. Yeah. But this equation didn't consider this. And actually, in a real application, we will manufacture this mechanism and to make their all R joint pointing to the same direction. They will all rotate about, let's call it Z axis, pointing out to the slides. Yeah. So there's assumption here. If we can consider this one as a planar mechanism, we know all these R joint, they are pointing to the same direction. If they are not pointing to the same direction, then it will be this case. In this case, well, it may not move. Yeah, this mechanism may just clock there. Yeah, and also the sliding. The sliding must also be on the surface. It cannot, well, you cannot just randomly change the sliding direction. Yeah. But this equation, this spatial equation for spatial mechanism, didn't consider the orientation of the R joint and the orientation of the sliding. And that's why it will cause a different result. But this result is not always wrong. In this spatial case where, yeah, this result is wrong. But in the general case, well, this result actually is correct. If the axes, they are not aligned, they are not parallel to each other. Yeah. So, and that's why we only consider planar mechanism. We mainly consider planar mechanism in our study. Because even in a real case, you see this one, well, if you build it, it's a 3D mechanism. It's not 2D mechanism. But when we consider this mechanism, well, we assume all the R joint, they are pointing to the same direction. So we make this assumption to make this spatial mechanism work like a planar mechanism. Yeah. Any questions? No? Really? Okay, so I think it's the last slide for today. So there's a term here we call inversion. Inversion is, suppose we have a 4-bar, well, not, it's also a 4-bar mechanism, but we usually call this one a crank slider or slider crank. It means there's a crank here and there's a slider here. Well, it's also a type of 4-bar mechanism because there's 4 links. And inversion means if we change the fixed reference frame or links, well, if we fix different links, then we will have different characteristics of a motion of mechanism. We'll just look at this example. So all these 4 cases, well, they are composed of the same links, hollow battery. So all these mechanisms, they contain the same links. They all contain 2 bar and 3 bar and 1 slider. But if you fix different if you fix different links, they will behave in a different way. So for example, the top one we fix this bottom link. And the second one we fix the second link. The third one we fix the third link. The fourth one we fix the slider. They are the same chain. If we consider mechanism as a chain, we haven't fixed anything. This one is we call it a chain. And they all belong to the same chain. But if you fix different links, they will behave in a different way. So for this one, we can make this work in 2 different ways. One is we use this bar tool, this link tool as the actuator. So we'll call this crank slider. So this bar tool you rotate and will transfer the motion into a sliding motion. So you rotate bar tool and this bar 4 you will move back and forth. And for the second case, well, we fix the link 2. And well, you can either use a bar 1 or bar 3 as the input. Let's say if I use a bar 1 as the input and bar 3 as the output, then bar 1 and bar 3, they will both rotate. Well, but they will rotate in different way. Input and output will rotate in different way. If I fix the bar 3, well, this mechanism, let's say if I fix bar 3 and I use the bar 2 as the input, so rotate this one and this bar 1 as the output, and you will move back and forth. It may also rotate. So the inversion is just a term. That means we use the same chain, but we fix different links, and we can make the chain to work in different way. It behaves like a different mechanism, but they belong to the same chain. Okay, any questions? No? Okay, so I think that's it for today, and I'll see you on Wednesday, not next week.